Nowhere are the challenges of working with robots in the wild or in the lab more clear, or perhaps I should say more murky, than when we talk about working on and in water. To work in a river, lake, or the ocean, every aspect of the robot has to be totally redesigned. The challenges are especially severe if you aim to have your mobile robot go underwater, where we would call it an autonomous underwater vehicle, or AUV for short. The body, energy supply, actuators, sensors, controller, and communication systems of an AUV all operate differently than they do on the land or in the air. Now, if you think about drastic differences in structure and function that you might see among fish, mammals, and birds, then you really get a sense for the differences that need to happen in how things function in the water versus elsewhere. So we're going to talk about 4 big differences that we have to pay attention to for the robotics of aquabotic things. So water and electronics do not mix, and that's sort of rule number 1 here. The problem is, got these robots going here. The problem is that water conducts electrical current. It acts like a wire, particularly salt water, which is 1,000 to 1,000,000 times more conducive than the fresh water that I've got here. So that can create pathways between electronic components that were not meant to have those connections. By creating those wires, we actually do something called short-circuiting the electronics. How many of us would be willing to drop our smartphone into a sink? It's not a good idea. So one of the things that goes on is you have to take a robot like this, which is an Aquabot built by Hexbug, and you have to very carefully compartmentalize whatever's happening inside. Now, these are little beautiful toys. These are autonomous robots, and what's really cool is they take advantage of the fact that water does this conduction to create a sensor, so that when I put this in the water, that sensor senses the water and actually starts the behavior of the robot up. So that's actually a very clever design to make use of what's happening there with the differences between operating in the air and in water. Now, I'm going to tell you a story of a mistake I made working with a beautiful robot called Robot Madeline, and I actually got in big trouble in water. So my research team at Vassar College learned the hard way what can happen. So Robot Madeline is actually built to go in the ocean, but we were testing her out in the pool. All her sensitive electronics are sealed in what we call bottles. These are containers that are sealed up with a double set of O-rings. And I had personally, before we were going to take Madeline over to the diving well, I personally checked those waterproof seals for grit, lubricated them with silicone grease, and then pressure fit those 2 main chambers. And then what we do is we apply a vacuum to those chambers, and when we seal up and stop that vacuum, we measure the pressure to make sure that that negative pressure relative to ambient can be maintained. That tells us that those chambers are sealed. Well, those seals were great, and when I stopped that, the negative pressure of the pump. And so I knew, okay, we were ready to go, no leaks. So we packaged up Madeline in her special container, took her over to the pool. Now, the thing about Madeline was we know that water's a problem, and so we had designed her to have sensors inside her waterproof chambers to detect leaks, very similar to the sensors you see here in these Aquabots. So in addition to just detecting those leaks, and we could get a message from Madeline if there was a problem, we also had programming on board Madeline that when she discovered it, she would very quickly come to the surface. Well, I had checked for leaks in the lab, and I made a fatal mistake though. I didn't check for leaks when we got to the pool. So I had done this many times before. It hadn't been a problem. What we figured out had happened was we think that during transport, those seals must have shaken loose a little bit. So we never had a problem before, and there was no problem until we had this particular problem. So what happened was Madeline was swimming underwater. She's a 4-flippered robot, and she flooded so quickly that there wasn't time for her to get to the surface. The electronic components were destroyed, all the computers on board and things like that. Lesson learned expensively. Now what's really interesting is you can actually get a robot like this Hexbug Nano that's built to be on land. You can actually get a little bit of behavior out of it when you put it in fresh water. So I'm going to pop it into the tank there, and it's not moving around, but I can feel on the tank that it's actually buzzing. So your robot might not die right away, and even if it survives, one of the problems you have to deal with is if you've made those metal contacts wet, eventually they will rust. So even when we build robots for being on the surface of the water, like this robot here, we have to take special precautions. This is a robot from my lab called a Nerd, and you can see it's made out of a food container, and so we took advantage of a top that is meant to be waterproof, and that seals pretty much everything around there and protects us from splashing. And so all the wires go down through a central hole here, so we wouldn't want to submerge the Nerd, but it is going to be splash-proof for us. Now I should tell you that NERD stands for Neuro Evolving Robotic Device. I kind of think that's the best name ever for a robot. Now let me just show you this Nerd working here since we've got it in the pool. We've actually got it designed so that it won't start swimming until we first turn off the lights. So I'm going to do the equivalent of turning off the lights here by putting a sort of hat over it. So now the Nerd is swimming, and you can see it's got a propulsive tail off the back, and it doesn't generate a lot of splash. So we're in pretty good shape this way. And it's got 2 eye spots, so it's built for following light gradients, and it's got IR sensors along the side so it can detect other objects that are swimming with it on the surface of the water. By the way, you can see what's happened with these Aquabots here. They stopped swimming. They have a timer after 5 minutes. And so I take them out of the water, put them back in, and there's a trigger for those Aquabots to start swimming again. And let's just see here, if I pull out the Nano is still working. But I don't recommend this because what's going to happen over time is it's going to actually rust inside here for our Nano. I love working with robots in the water. I think the challenges make it really interesting. So we've talked about the challenge here of what goes on when you've got water mixing with electronics. And now we'll talk about the electronics themselves. Let me clear this away and we'll get to sensors underwater. All right, let's talk about the second difference between working in water and working in air or on land. The sensors we use in air on land and land often work poorly or not at all in water, and here's why. Radio waves work well in the air, but they don't work well underwater. The problem is that the frequencies that work well in air, which are about 10 centimeters to 10 meters long, those are normal radio waves, as soon as you put them in the water, they don't work. They attenuate. So we use them well in the air, but when we put them in water, they don't work. So we can't use radio waves. We have to use something else. So this is one reason submarines need to come to the surface occasionally. They need to come up and communicate and then get navigational fixes using those radio waves. Now, radio waves are part of the electromagnetic spectrum, which also includes microwaves, infrared waves, which we've talked about with sensors with infrared emitter and detectors, visible light waves, and so on, each of which are shorter than those radio waves. Now, visible light also has problems penetrating the water. Oceanographers refer to the region where visible light penetrates sufficient for photosynthesis as the photic zone, with a cutoff point defined where less than 1% of visible light from the surface can penetrate. That distance, where over 99% of the light doesn't get through, is only down to about 200 meters. So in order to propagate long distances in the water, electromagnetic energy needs a wavelength of over 100 kilometers. That's long waves. These are extremely low frequencies, right? And they've been used actually for communications with submarines. But it's a real challenge. Those low frequencies mean that messages have to be short. And they can only be one way from the station, which is on the land, to the sub, because you need a huge antenna to create those giant waves. And even a submarine, a big one, is too small to be able to generate a wave that is that long, or to carry an antenna that's long enough to do it. A different kind of wave that does travel well underwater is a pressure or acoustic wave, sound. Submarines can communicate while underwater using acoustic transmission systems with a speaker and a hydrophone. But these pinger systems, very much like the pingers that we talk about in air, we can use sound systems as well as air, they only travel short distances. So they suffer from noise created also by reflections and other noise that's in the water. So we get attenuation. Those particles can scatter, the pressure waves can scatter off of particles in the water. Also, the amount of information that you can transmit with a pinger is very small, since all that you can vary to represent information is the pattern, the pulse of the sound, the rhythm. An underwater acoustic modem system is the most often used form of communication in underwater marine robotics. Now, the most sophisticated systems offer short-range communication over the range of 1 kilometer in shallow water situations. Now, the rate of data communication is up to 30 kilobits per second. Now, this is pretty slow compared to wired or wireless transmission rates on land. A few dozen kilobits per second was already possible on land with a cable back in 1942, with an early modem developed by IBM. These days, my own wireless modem at home communicates at speeds of up to 300 megakilobits per second, so it's 10,000 times faster than an acoustic modem that you'd find in the water. We've talked about acoustic modems as a standard way to communicate wirelessly underwater. You can also use a wire, a communications tether, and that's very common as long as your robot is working very close to the ship that's controlling it. In the first version of Robot Madeline that we built, we actually controlled her with a remote control cable. And as long as you don't have to have your robot swim very far away, a communications tether can give you great control over your robot. Using a tether to communicate with an underwater robot allows you to do jobs like you can inspect ships' hulls, underwater storage tanks, bridge pilings, and dams. And you can also scan a coral reef from your boat, which is pretty cool too, right? So underwater robots with a tether are much more likely to have remote control and/or energy supply coming through that tether as well. Now, let's say I'm using a 500-foot long cable for a search and recovery mission in near-shore waters, shallow waters. What's really important here is if the robot is at that depth, I probably can't look over the side and see where that robot is. I have to rely on a bunch of onboard sensors to help me keep track of where I've got that submarine going. Now, local sensors operating over short distances also offer a creative way around the limitations of radio waves, acoustic signals, or tethers. Here's a really cool solution that has been prototyped by European roboticists in a project called COCORO, which stands for Collective Cognitive Robotics. The idea they have is to use blue light to flash communications between robots underwater. The distance of communication is achieved by a bucket brigade approach. Use a swarm of robots arranged in a linear chain. A signal at one end propagates from one robot to another robot to another robot along that chain. So a COCORO system, for example, could have a search and rescue swarm with some robots at the bottom of the ocean looking for a plane's black box, for example, and others scattered through the water to the surface, and then you have a surface robot that communicates with people on a ship or a satellite via radio waves. Even though COCORO uses blue light for communication, just like all the other kinds of signals except the acoustic one underwater, that signal of light degrades very quickly with distance. So in fact, the real innovation is to show that a swarm of robots arranged in a line can extend communications to new lengths. And in fact, they can use light or they can use radio at those small distances as well underwater. This swarm-based collective communication system is still in the earliest stages of development. A common replacement for vision underwater is sonar, which stands for Sound, Navigation, and Ranging. This is another use of sound underwater, by the way. With active sonar systems, the sensor sends out a sound pulse or train of pulses and then listens for the return, what we call the echo, right? And depending on how long it takes that pulse to return and how strong the signal is, the robot can use sonar to detect objects underwater and to map terrain. For example, the PAVE robot has a 3D sonar that looks forward and a 2D profiling sonar that looks down. PAVE stands for, by the way, Prototype Autonomous Inspection Vehicle. PAVE has a navigation system that includes a compass and inertial guidance sensors. PAVE also has an acoustic communication system, and yes, it does have a camera and lights to be able to gather pictures where it's dark. The reason to carry what might seem like redundant sensors sonar and camera, is that they work well together as a team. Sonar is great for murky waters, object detection at a distance, and for measuring the shape of complex surfaces. A camera is better for close-ups and for identification of what certain types of objects are. Now, the PAVE robot was jointly developed by Subsea 7 and Seabite, and as I mentioned, it stands for Prototype Autonomous Inspection Vehicle, so it's still under development. PAVE is a large hover-type robot weighing over 700 pounds in air and able to dive to depths of 1,000 meters. That's pretty impressive. Battery-powered, the goal with PAVE was to develop new methods of close maneuvering that could be done autonomously. So get rid of that tether and let that robot operate by itself. And the key to autonomous movement is to link information from sensors to the control of actuators. And because sensor-guided movement is at the heart of autonomous robotic behavior, the choice of those sensors is a very important part of the design. As we've seen, sensors underwater face a number of challenges because of the physical properties of water and operating in the wild. Video systems, for example, only work if the water is clear and light is available. Go into murky waters of a delta or into the deep, and you are in trouble if you are relying on vision. The mission concept for PAVE is to operate as an autonomous inspection system, as the name implies. For example, we humans have sunk all kinds of electrical and communications cables in the oceans and lakes, and these cables need constant maintenance that can be directly assessed by close-up inspection. So PAVE locates the cable riser using sonar, and then using sonar up close, it moves along the cable, delivering video images of the cables, and then floats along the way that a topside human can review. So sonar is clearly the primary sensory system for this system. Now keep in mind that sonar is augmented by the onboard compass and inertial guidance systems to keep track of heading and the distance traveled. PAVE can navigate to the bottom and inspect pipelines that are along the bottom. And one of the virtues of autonomous robots like PAVE is that because they lack tethers, they can move in and around complex three-dimensional structures without fear of tangling. Like PAVE, the very first underwater robots lacked tethers. They also did not communicate with humans once launched, so they operated autonomously. Let's talk about the next big difference between operating robots in air or on land and underwater. The bodies of aquatic robots have to be very different, and they form a distinctive group of robots. The first autonomous underwater robot was a torpedo. Now, while torpedoes are weapons, the physics that makes them torpedoes and makes them efficient has inspired a whole body type among modern autonomous underwater vehicles that are used for many other purposes. In the search for the missing Malaysian airliner in 2014, torpedo-shaped underwater autonomous vehicles were used to scan the ocean floor in search of debris. Bluefin Robotics has a torpedo-shaped AUV called the Bluefin 21. The tail doesn't have the protruding control surfaces of your standard whitehead torpedo, no rudder, and no elevator. That sleek design reduces the chances of the tail getting hung up on cables, seaweed, or things like that. Now, the torpedo shape tells us a lot about the physical challenges of moving in water. A torpedo is an example of a streamlined body. A streamline is a visualization technique to see how smoothly the water moves around a body as that body moves through that water. Shapes like torpedoes, or robot Madeline for that matter, are tapered in the front and the back to make for very smooth waymaking through that water. They're said to be streamlined, which means they're more energy efficient to move. In contrast, an unstreamlined shape would have blunt ends and be boxy in shape. This means that you can tell right away when you look at an underwater robot if it is built to cruise, like a torpedo, or to hover. Cruisers are streamlined and hoverers are box-like. For its torpedo-shaped robots, Bluefin has designed the tail cone as a ducted thruster that is articulated. So that connection of the tail cone to the hull is like a ball and socket joint. A swiveling joint like this gives 2 degrees of freedom for the adjustments of thrust. That tail cone can pitch or yaw, or move in some combination of those two. The AUV steers by rotating that tail cone to direct its thrust in different directions. Let's take a moment to learn how the three-dimensional motion of ships is characterized using 6 independent degrees of freedom. We use 3 degrees of freedom that are in rotation: pitch, yaw, and roll. So pitch, yaw, and roll if I'm a vehicle. And we use 3 translational degrees of freedom: surge, sway, and heave. So let's see if I can do this. Surge is forward and backward, sway is side to side, and heave is up and down. There, now you can start to speak like a pirate. Aye, the ship, she's rolling. Arg, damn the torpedoes. Actually, let's not damn the torpedoes. They're actually very interesting robots. And the Bluefin 21 is built for deep water surveys and search and rescue. And it was used, as we mentioned, to help search for the Malaysian Airlines Flight 370 in 2014. Smaller torpedo-shaped AUVs, like the Bluefin 9 and 12, are built for shallower operations. There are 2 categories of autonomous vehicles that we haven't talked about yet: the spray glider, which looks like a torpedo with wings, and the H AUV, where the H stands for hovering, and AUV, of course, stands for autonomous underwater vehicle. The type of body in an H AUV is called an open space frame. What all these AUVs are designed to do can be understood by looking at what sensors are available on Bluefin's version of an H AUV. Choosing different sensors lets you customize your AUV for that particular job that you have in mind. There are imaging systems that include cameras and sonars that you would use for mapping tasks. There are navigation systems that include compass, GPS, and inertial navigation systems that work by detecting the acceleration of the AUV. Scientific sensors include things like a CTD sensor, which measures conductivity, temperature, and depth. And remember, we're interested in conductivity, and it's measured because it's the ease of passing of electrical current through water. And guess what? It's used as an index of salinity. So we're interested in it because of that, our worry about electronics, right, and flooding our compartments. But it's also a basic property of water that we want to keep track of. So as we mentioned, salty water conducts electricity even better than fresh water. Now, temperature is measured with a sensor called a thermocouple, which uses the flux of heat across the sensor to measure temperature. Depth is measured with a force transducer, a device that changes its electrical resistance as it is deformed by the pressure of the water. AUVs also have a variety of ways of communicating with their topside operators, including, if they are at the surface, direct radio frequency and satellite uplinks. Let's peek inside the navigation systems to see how AUVs are getting around. Dead reckoning is a very common way of navigation. In dead reckoning, you start by knowing where you are. An AUV might get its coordinates from GPS at the surface, and then it dives. While submerged, the AUV uses its compass to head in a particular direction. It keeps track of how far it has gone using a sensor suite called a Doppler velocimeter log. It uses Doppler effect to measure the motion of the bottom as you're moving past it or through the water column relative to the motion of the AUV. In water, as in air, once you have your heading from your compass and velocity and the time that you've been at that heading and velocity, you can estimate where you are relative to where you started. You have to know what that is. So you need eventually a navigational fix, and a navigational fix is short for fixed position. And Bluefin AUVs get this by surfacing and using GPS, the global positioning system that's provided over high-frequency microwave signals by satellites. This approach allows for autonomous operation out at sea and in constrained environments like harbors. Another way to estimate how far you've traveled is using a sensor suite called an inertial measurement unit, or IMU. And we mentioned it without explaining before what we were talking about with the PAVE robot. This sensor has kinematically independent accelerometers and gyroscopes to estimate velocity and orientation in 3 dimensions. Submarines often use a similar set of sensors. All right, so that covers a whole lot of territory here. And let's get on now to a final difference between operating robots in the water and operating them in air and on land. And that has to do with energy supply and actuators. These have to be very different as well. Bluefin's torpedo AUV works using batteries. and they have a mission life of about 24 hours, and that's pretty impressive. And that's great for mapping near shore, but there are times when you want your AUV to have missions that last even longer. For example, extensive monitoring of sea surface temperatures, which is vital for predicting El Niño events, for example, requires time on station that we would measure in weeks or months. One way to extend mission time is to reduce the amount of energy that you spend on propulsion. You might even decide to just float along with currents or tides, but then you aren't an AUV because you aren't self-propelled. You'd be a sensor buoy that floated along and collected data. Now, a very clever way to be self-propelled, but to do so with minimal cost, is to glide. And then here's where those Slocum gliders come in that we mentioned, that class of AUVs that look like torpedoes with wings. So Bluefin has a spray glider, they call it, and gliders are very efficient and they take very little energy to operate because they can operate on differences in buoyancy and don't need a propeller. They can run on a single mission for over 6 months. And let me tell you about the secret of making a glider work. I mentioned buoyancy differences. Gliders work by changing their density relative to the water. An object that is more dense than water we call negatively buoyant, and it will sink like a stone. An object that is less dense than water we call positively buoyant, and it will float and rise. So what a glider does at the surface of the water is make itself negatively buoyant, so that it sinks and uses that sinking motion to allow it to move forward thanks to its wings. This kind of controlled gliding is just like what we see in electric rays. But unlike an electric ray that is always negatively buoyant, an AUV glider gets to the bottom of its downward glide path and then it changes its density. The glider is able to become positively buoyant, which causes it to float upwards, and again, it uses its wings to convert that vertical motion into a forward glide path. Most of the energy of propulsion in a glider comes from this gravitational effect. So we talk about these AUVs as having a buoyancy engine. I say most of the energy because it does take some energy to change the density. What has to happen is that AUV pumps mineral oil back and forth from an internal to an external bladder. When the mineral oil is in the external bladder, the density of the incompressible aluminum hull has been decreased below the density of water, so its buoyancy becomes positive. Pretty cool trick, huh? Now, when the oil is pumped back inside the hull, its density has increased to more than the density of the water, so buoyancy becomes negative. You can think of a buoyancy engine as sinking a ship by flooding one of its compartments, and then floating a ship by bailing out that same compartment. This idea was patented by Ian Fallon in 1965. He was inventing a vehicle for divers, but the basic propulsive mechanism works for diverless AUVs too. And it works incredibly well. In 2009, RU-27, a modified Slocum glider AUV, which was dubbed the Scarlet Knight by the Rutgers engineers who built it, became the first robot to cross the Atlantic Ocean underwater, transiting from New Jersey to Spain in 221 days. Very cool. And when it traveled, it took data on sea temperatures and water conductivities. Sound familiar? Gliders are the long-distance, low-power champions on the opposite end of the AUV spectrum from the hovering AUVs like the PAVE robot. Hovering AUVs are vehicles designed not to go very far at all, but to just run for a few hours. These are hovering AUVs like the HAUV from Bluefin. Hovering AUVs perform close-up inspection of hulls of ships, submerged piers, or rocky bottoms. To hover and hold station, they maximize something that gliders and torpedoes are very bad at: maneuverability. The HAUV inspected, for example, the USS Constitution, and I can survey in the same lawnmower pattern that the Bluefin 21 used, using its sonar to scan the complex three-dimensional geometry of the propeller of a different ship. So most hovering AUVs, like the ships that they survey, rely on propellers that spin. These are small propeller-based thrusters, and they are usually set up in opposing pairs to generate the countervailing thrusts that allow them to so precisely maneuver. The champion of long-distance and long-duration robots is Wave Glider. Built by Liquid Robotics, it looks a lot like a surfboard with a couple of antennae. Now, what makes Wave Glider such a nifty example of robots in the water is a completely novel kind of propulsion. Wave Glider has two main parts. The float is a lot like a surfboard, and it floats at the surface. And it carries with it a solar panel to charge batteries that power sensors and communication systems. The other part of Wave Glider is the sub. The sub is part of the propulsion system, and it's inspired, by the way, by the flukes of whales. Now, if you gently push on the wings of the sub, what happens is they will tilt down but not up. If you're going to try and pull the sub up vertically in the water, the wings would all tilt down and then deflect as you were trying to pull it up. If you are a swimmer or a paddler, you may recognize this process as what we call sculling. What is functionally significant about sculling is that we move the wing or the paddle in one direction and we generate thrust perpendicular to that direction. If you look just under the water, right where the Wave Glider 3 is being deployed, you can see a whole set of what look like wings. Those wings are lowered down, kept attached to the surface vessel by a flexible umbilical cord that the sub is connected to. Now, here's where that magic happens. Waves power the Wave Glider. When a surface wave moves that surface vessel upward, it pulls the wings upwards too. If those wings are angled correctly, they can, like the wings of a glider, pull the surface vessel forward. So get this, all of the power of propulsion is supplied by waves. In 2013, a wave glider named Benjamin Franklin completed a journey of nearly 8,000 nautical miles. Benjamin survived shark attacks, overcame severe currents, and ended his travels navigating through a cyclone to reach the southernmost part of the Great Barrier Reef. Benjamin arrived at Lady Musgrove Island near Bundaberg, Queensland, Australia on the 14th of February 2013. On May 15th of that same year, Benjamin was awarded the Guinness Book of World Record for the longest journey of an autonomous surface vessel. Robots at work on and in the water differ from other robots in design and purpose. They offer us remote presence at depth beyond what we humans can withstand. And they work autonomously to map the seafloor and act as our first responders in search and rescue. Autonomous aquatic robots serve as our mobile sensors, monitoring ocean conditions and marine wildlife. The unstructured environment of the aquatic world offers tremendous challenges to roboticists. And when those challenges are met, they can lead to unique solutions and some of the most exciting robots on the planet.